The Space Shuttle story actually began more than 43 years ago, even before astronauts Armstrong and Aldrin kicked up the lunar dust for the first time. It was 1968, and President Lyndon Johnson was struggling to deal with an escalating conflict in Vietnam. Anti-war protesters carried out violent demonstrations across the country, and two of our most promising idealists, Martin Luther King Jr. and Robert F. Kennedy, were gunned down by fanatics. But in theaters across America, Stanley Kubrick's 2001 A Space Odyssey offered moviegoers an escape from the commotion, if only for a couple of hours. Kubrick's movie presented an imagined future where passengers in winged vehicles traveled back and forth to a space station parked in Earth orbit. What the general public didn't know was that NASA was already hard at work, making part of Kubrick's vision a reality. NASA engineers were working to design a reusable space vehicle, one that could carry astronauts into orbit and return them safely to Earth by landing on runways with wheels, like conventional aircraft. That sort of science fiction technology was anything but conventional in 1968, and for the men and women who worked on the shuttle's design, the undertaking was enormous. George Ware came to NASA Langley in 1953. He remembers testing space shuttle concepts in the early 70s that were very different from the design we're familiar with today.
To have a reusable system, we would have a carrier vehicle and an orbiter. The carrier vehicle would take off either horizontally, sometimes vertically maybe, and then take the orbiter to altitude, release the orbiter flies to orbit, the carrier vehicle returns to the landing site and is refurbished for use again. The orbiter completes its mission, flies back, lands at the site, and the system starts over again. It became apparent soon that this was going to be a very expensive system to develop. These two different vehicles, an orbiter vehicle and a booster vehicle. So eventually the concept digressed, if you like, to a system that lost parts.
Those lost parts were the shuttle's external tank and the two solid rocket boosters. One feature that didn't change was a requirement that the orbiter perform both as spacecraft and aircraft. Tom Yeager spent his entire 44-year career at Langley's Aircraft Landing Dynamics facility, studying aircraft ground handling. Since the space shuttle would return to Earth like an airplane, Yeager's group was consulted on the design of the runways the shuttle would use, and also the tires on which it would land.
I first got involved in probably 75, 76. It sent out to our facility the nose landing gear itself. And so we strapped that on our test carriers and did probably 100 runs looking at the nose gear and how it behaved under different steering angles as well as different speeds, and also under dry and wet conditions. The shuttle itself, with its speed, did develop some spin-up patches on the main gear tire when they touched down on the grooves. It wore through like one, possibly two plies of 16 that were available on the main gear tire. So in that regard, we looked at ways to change the touchdown area to reduce the texture and eliminate the grooves. And after that, the subsequent landings occurred without any tread wear. Of course, that little patch, which was only about 3 inches in length and maybe 2 inches wide, was a weak spot on the tires, and the astronauts didn't want to have any weak spots.
In April of 1981, with the whole world watching, astronauts Bob Crippen and John Young climbed aboard Space Shuttle Columbia for the very first flight of NASA's new Space Transportation System, or STS-1. For the Langley engineers who had put so much of themselves into its development, this was a trial by fire.
These guys, Young and Crippen, flew this vehicle for the first time. There was no build-up to that flight. It had to work the first time. The vehicle flew on aerodynamics, so essentially we felt like we owned the vehicle. It was our numbers that were flying that vehicle, so we had a very big input into that. And therefore, there was some bullets sweat during the launch, and particularly the entry on that. How good did we do? These guys are up there flying on our numbers. And fortunately, we were pretty close. We were very, very pleased with that result, and I'm sure those guys were too.
Now, the first 5 or 10 landings, they wanted me to be on site to look at the tires after each landing. And so that was a game, because I go to Kennedy, and of course at the last minute they decide, well, we're going to land at Edwards, and there's no way I could get to Edwards. And,
With few exceptions, those early flights went as planned. With each successive launch and re-entry, NASA engineers were tweaking and adapting their designs and procedures. Over the more than 13 years that the Space Shuttle was in development, and 30 operational years, NASA Langley Research Center made significant contributions to the program. They include development of the shuttle's thermal protection system, flight control and guidance studies, launch abort and crew bailout procedures, and the development of the glass cockpit. Researchers and engineers at Langley also developed and flew a number of experiments aboard the shuttle. One such payload was the LiDAR in-space technology experiment, or LIGHT, flown aboard Space Shuttle Discovery in September of 1994. Melvin Farabee was on the LIGHT project team.
And I had the honor of being on console as a mission planner for the mission. I got to plan when the instrument took data. We predicted where the shuttle would be at a specific time, and then relayed those times to the mission controllers and the instrument controllers, where now you're going to turn the instrument on, now you're going to turn the instrument off. It was the first time that a laser had been flown in space specifically to determine the structure of clouds. I never thought that I'd be in a position where I'd be on console during an actual shuttle mission. That was a real big high point in my career.
There were many high points in the 3 decades of the Space Shuttle program, which will go down in history as one of mankind's greatest achievements. But success sometimes comes at a cost.
Challenger, go with throttle up.
The Challenger and Columbia tragedies twice forced the program back down to Earth, and served to remind everyone how potentially dangerous going to work in space could be. With the loss of Columbia and her crew in 2003, NASA was presented with a clear objective. An accident like this should never be allowed to happen again. Once the underlying causes of the mishap were understood, it was time to go to work correcting them. Langley engineer Barry Meredith was sent to Johnson Space Flight Center to focus on the return to flight effort.
Tragedies have a tendency to bring families together. The Columbia accident did that to NASA. It became immediately apparent by the nature of that accident that the critical skills at NASA Langley, I'm speaking of aerothermodynamics, structures, materials, would be directly applicable to the accident investigation as well as the subsequent return to flight effort. The best and the brightest were immediately available, regardless of what their nominal responsibilities were. They were immediately available to apply to the top priority of the agency, which was returning to flight.
That priority sent many scientists and engineers at Langley and elsewhere back to the drawing boards. Columbia had been lost due to a compromised heat shield. To avoid similar catastrophes in the future, NASA Langley engineers developed a new procedure that involved using an infrared camera to perform a full inspection of the entire thermal protection system, both tiles and wing leading edge, after the shuttle reached orbit.
Now, this camera was developed in a very aggressive schedule, so much so that when it was presented to the shuttle management, it was deemed too aggressive to be feasible. Mike's team took that as a challenge and indeed identified, developed, and certified that camera on that schedule. It was really a heroic effort.
After Columbia, it seems somehow fitting that STS-114, NASA's much-anticipated return-to-flight mission in 2005, featured 2 astronauts with Langley ties, mission specialist Charlie Camarda and Steve Robinson. Before he became an astronaut, Camarda had worked as a Langley thermal structures engineer for 22 years.
This was deeply personal to the people at NASA Langley. So there was a lot invested in Langley's contributions, more than just technical. It's one of our own up there that we want to make sure he comes back as healthy as he left. And to watch STS-114 go up as the return to flight mission was extremely emotional, no question about it.
With newly revamped equipment and procedures, the most complex machine ever built would indeed return to flight. In all, 22 additional missions would be successfully flown. Stemming from the Columbia accident, but also to gather data to help design future spacecraft, Langley researchers proposed the HITherm, Hypersonic Thermodynamic Infrared Measurement Program. The idea was to capture thermal snapshots of the shuttle as it re-entered the atmosphere. Debbie Tomek was the project manager of HITherm.
We were kind of this crazy team that wanted to, image the shuttle during re-entry. These Langley researchers coming in and, we were working with the program managers there. They gave us a spot in mission control stage out of there and everybody was excited about it, but nobody thought, there's no way they can track the shuttle. Coming in at Mach 22, trajectory can change up to the last minute. These people are crazy. Well, you know what, we did it.
And they didn't do it just once. With the help of a U.S. Navy unit flying specially modified aircraft, the HITherm team surprised nearly everyone and successfully imaged the shuttle during its re-entry phase 7 missions in a row. The results in terms of collecting boundary layer transition data and thermal signatures were truly groundbreaking.
You look at the data that we got, and it's just absolutely fascinating, the contribution not only to the shuttle program and understanding, what was going on with their flow fields, but also taking that data and equating it to future designs. I mean, what we took out of there is data that's going to help us build better heat shields, can help us build better vehicles.
With the manifest complete, STS-135 would be the last mission for NASA's Space Shuttle program.
Nose gear touchdown. Having fired the imagination of a generation, a ship like no other, its place in history secured, the Space Shuttle pulls into port for the last time.
As Atlantis touched down for the final time at Kennedy Space Center, many NASA Langley employees, past and present, felt a deep personal sense of pride.
When they announced we'll stop the shuttle commander during STS-135, and he, said, "This, you've inspired a generation." That's us. It indeed has inspired a generation. So for me to see that end was very emotional. But to have been a part of it, I feel privileged.
It's kind of melancholy. However, the future's bright. The future's bright. We're looking to go somewhere else, and you got to stop doing what you're doing in order to move forward.
And move forward we will.
NASA's mission is to go beyond low Earth orbit. And that's where we should be, that's where we should go. And hopefully in the very near future, we will see a more definitive plan and mission and funding commitments to make something big in exploration happen. And I hope I'm still around to see it.
We're trying to put ourselves in position to go to the moon, to an asteroid, a near-Earth object, or to the moon or to Mars and beyond. In my current position in space technology, we're trying to develop all of the building blocks that we need to send people beyond the low Earth orbit.
We've been in the business of spaceflight for 50 years. It's what we do for NASA. It's what inspired me as a kid. It's what got me here. And there's thousands and thousands of others just like myself. I think it's staying our course, and it's going back on what we're good at. We're good getting down in the trenches and figuring out problems and solving them. And I work with so many people that share my passion. To me, that's a privilege to be able to do that. And I have a lot of faith that we will get back there, and sooner the better.